My next speaker is Fumio Hiai from Tohoku University, and he'll be talking about quantum f-divergences in von Neumann algebras.
Thank you very much. First of all, I would like to thank the organizers for giving me this opportunity to give a talk related to the respect. This is my first time for the Beyond I.I.D. So the Danish is 5 years younger than me, so his passing away is really too early for me. So there are two pictures here. This one is when I visited his home nearly 25 years ago. The Danish looks young. I am also young. And this one, I have good memory. The Danish and I organized the Hungary-Japan joint project twice. So he came to Sendai many times. Once he came to Sendai, Professor Takesaki invited us to his cottage near Zao Mountain, and Takesaki's wife recommended us to join the walking tour traversing the Zao Mountain, and this picture is on that occasion. And Danish put this picture in his homepage at his picture, so you can easily look at this picture at his homepage. So I guess he considered this picture as his best picture. Okay. So here is the brief history from my personal point of view. In 1962, Umegaki, my supervisor, defined the relative entropy in the semi-finite von Neumann algebras. The 73, this is the Lieb's very famous paper on the convex trace functions, and the Lieb-Laskide proves the strong subadditivity. And 76, 77, Araki extended the Umegaki relative entropy to general von Neumann algebra. And the 82, the Kosaki used the complex interpolation theory to extend the Wigner-Dyson-Lieb concavity. He treated the formula, this form of quantity. That is exactly the the K-psi entropy discussed in 85 and 86. Kosaki discussed only joint concavity to extend the Wigner-Dyson-Lieb concavity, but the Danish discussed more property, the motonicity inequality and other properties. So now Kosaki's variation expression for the relative entropy, the 86, that is very nice. And the 1989, I think, the Nagaoka told me his dream to prove some problem. And the Pets first visited to Japan by Oya's invitation. I met Danish, and I mentioned the Nagaoka's problem. So he immediately claimed that that is his that was his own problem. So we collaborated to settle the problem of the Nagaoka's problem. And 1992, the PET stayed for 10 months in Kyoto University as visiting professor by Araki's invitation, and he delivered a long series of lectures, and that resulted in the famous Oya textbook. By the way, the Masahito Hayashi attended the lectures as a student. And the 1992, I got some idea that to use the hanging up LP spaces. I considered this kind of problem, and this is relative entropy, and it looks the usual Meraki definition, but this is general Fumio algebra. So H rho and H sigma is not the density operators, and the hanging up L1 element, and the TR is not the trace, and hanging up the trace functional. So I consider this expression, and also the lower upper bound, the motion is lecture disappeared in the last part. I consider this part in the Fumio algebra setting. But finally, I didn't publish the paper, and yeah, many years later, we wrote these two papers, the Moshoni and Peyton. And 2013, some kind of breakthrough happened on the sandwich range divergence by these authors. And very recently, the 2016, the paper published this year, Berta showed to Tomamihira and Yenchoba the extended the standard range divergence, sandwich range divergence to the Fumio algebra setting. That motivated me to consider my old problem, 26 years later once again, and for me time passed so fast. So now this is a plan. After some preliminary from Fumio algebra, I would like to standard F divergence and Rényi divergence and maximal F divergence. So first, the standard form. Standard form and relative modular operator are essential to introduce the standard and maximal F divergence in general Fumio algebra setting. So M is Fumio algebra. That is interstar subalgebra of B of H, closed in the weak operator topology. And the M star plus is the normal positive linear functional. That is the positive cone of the predual of M. Yeah, here is some note. For example, the Fumio algebra is type 3. If we restrict any small piece of Fumio algebra M, any corner of the M, you don't have the trace. So there's no trace. There's a trace nowhere. So we cannot use trace. We need the standard form and hanging up LP space technique in that way. So the hanging up introduced the standard form the quadruple M that is represented on the Hilbert space H and with conjugate linear involution H and the self-dual cone. That's called natural cone, satisfying these four properties. And the standard form is the unique up to unitary conjugation. That is very nice. And for every normal positive linear functional, there exists a unique C sigma that is vector representative, and the sigma is implemented by the vector representative C sigma in this way. And we use the M support SM sigma and M prime, M commutant support SM prime sigma. Those are the projection onto these closure of this part and the closure of this part. Then to extend the relative entropy to general von Neumann algebra, I like to introduce a relative modular operator in the following way. For two normal positive linear functional rho sigma, the conjugate linear closure operators S rho sigma and F rho sigma are defined in this way. This is usually the unbounded but the closable operator. So the relative modular operator is defined to be the adjoint of S rho sigma, that is closure of F rho sigma, times the closure of S rho sigma. Then the polar decomposition of the closure of the S rho sigma is given J times the square root of the relative modular operator. Here the unitary part is the independent of the choice rho sigma, and the J appears. J is the involution in the standard form. That is very good point. And the support projection of the relative modular operator is the M support of rho times M prime support of sigma. And we write the spectral decomposition of the delta rho sigma in this way. The spectral resolution I wrote E rho sigma. So maybe many people are not so familiar to the general von Neumann algebra. In that case, please consider the matrix algebra M, the represented on the left multiplication by the MD itself that is the Hilbert space with the Hilbert symmetry inner product, and the J map is just the adjoint map and the positive semi-definite operator. That is for natural cone. In the V of H case, type 1 case, this MD Hilbert space is just we take the Hilbert Schmidt operator with Hilbert Schmidt inner product. So this is easy to consider. So to define the high-up LP space, we take this is rather the big mathematical machine, but anyway, we take the cross product of the given von Neumann algebra by the modular orthogonal group. That is the semi-finite von Neumann algebra with canonical torus tau, and with dual action satisfying scaling property. Then for any point of P, we can define the hierarchy LP space, the tau measurable operator affiliated with N satisfying this scaling condition. And in particular, when P is infinite, this is equal to the theta fixed point algebra. That is exactly equal to the given M. That is a part of the Takesaki duality. So Then the predual M star is canonical order isomorphic to the hanging up L1 space. So we define the map from predual element functional psi to the L1 element H psi. And also we define the TR functional on the hanging up L1 space by taking the TR functional of H psi is equal to psi psi of identity, evaluation of at identity. Then for positive P, LP hanging up LP norm is given this way, and the LP LQ duality is given here. And in particular, P is equal to the L hanging up L2 space is Hilbert space, and then the phoneme algebra M and the hanging up L2 space and the adjoint map on L2M and the positive part of L2M. This quadruple is the standard form of M. The standard form of M is unique, so we always this quadruple as a standard form. This is the rather tractable standard form. And the functional sigma has the vector representative, the hanging up L1 H sigma, the square root of H sigma. H sigma is L1 element, the square root of H sigma is L2 element. So this is the normal functional sigma is implemented in this way. Now I want to introduce the standard divergence. So f is the convex function on the open positive half line, and we consider this convention. The b of f, b times the f of a over b, that we consider that in the special case a is equal to 0 or b is equal to 0. We take this convention. And we also define the transpose of f, f tilde, t times f of t inverse. Then the boundary point, these two boundary points we specify. The two boundary point is exchanged under the exchanging the f and changing the f to f tilde. So this is the definition of case the standard f divergence. So specializing the Denish's case I entropy, and with some suitable modification, we define the SF, the standard f divergence, this way. So two boundary values, and integral in terms of the spectral decomposition of the relative modular operator. By the way, Danish original definition of case entropy, that is a little more general, but his definition, this part is missing. And he considered mostly the operator Morton function. Operator Morton function is operator concave, and the minus f is operator convex. So here we consider the operator convex function. But anyway, the integral is from 0. So this part is the Danish definition. But I think this part should be necessary. So our standard divergence has the basic property, the star isomorphism invariance and homogeneity and additivity under the direct sum. And when the rho and sigma, rho of rho and sigma is exchanged, we obtain the SF is equal to SF tilde. The F is transpose of F. So F and F tilde is the symmetric situation. And most typical example of the standard f-divergence is relative entropy. In the case of function f is t long t, that is the semi-finite case due to Megaki, and the linear case due to Araki. Now I assume the function f is a little more restrictive, the operator convex function. And the Lesniewski-Laskai's paper, this integral expression is given. We use this canonical integral expression for the general operator convex function on the open positive half, right? Then the first theorem is co-circuit, the extension of the co-circuit variational expression to the general standard f-divergence in this way. So this is variational expression, the double supremum of an integer, positive integer, and the supremum, the L-valued, finite valued L-valued step function. Here the L is the subspace of M, the density in M with respect to the strongest operator topology. Here the Fn appears. Fn is Fn is defined the integral domain, the cut off by this way, 1 over n to n. The cut off the interval, and a little modified the two terms, coefficient c terms and the d terms this way. Then the Fn is increased to F, and the Sfn increased to Sf. And the cutoff function Fn is given the linear term minus Hn. Hn is defined this way with measure nu n is defined here. And Sfn is from this linear term we have this term, and from this minus this integral. Then the Kosaki obtained his variational expression for relative entropy. But to do that, he go to the rather general variational expression for the operator monotone function. Our Hn is operator monotone function. This is Kosaki's variational expression. So we insert this expression into this. Then we finally obtain this formula. So this is a double supremum, and not so beautiful mathematically, but this is very useful. And here the linear term and the minus integral, the minus infimum, but the outside, then the outside the infimum, here the supremum change to supremum, the minus here. This part is also linear, and the extension. So this big bracket function is the linear function of sigma and rho. So this formula is a kind of linearization formula. Okay. So from this, the generalized Kosaki's variational expression, we can immediately obtain the most important part of the standard f-divergence, joint lower semi-continuity. That is the weak topology. The lower semi-continuous in the weak topology, and the joint convexity, and the order relation, and the monotonicity inequality, or data processing inequality, and the martingale convergence. So for example, the martingale convergence, we take the dense subspace, we take just this the union of M alpha. then this martingale convergence is immediately follows. And the special case of the Morton inequality is the pi-RS volume of inequality and the strict positivity and the convergence property. Everything is the immediate from the variational expression. So this variational expression, even very useful in the even in matrix case, I believe. And finally, this theorem is a kind of martingale. But here we take increasing projection and we restrict to the functional to the reduced formal algebra E alpha M E alpha. So this is martingale convergence, but this is not included in the previous one because the reduced formal subalgebra is not unital. So this needs the independent proof anyway. So this is, for example, the type 1 case, V of H case. This is a very nice formula, I guess. Next, Renyi divergence, standard Renyi divergence. So we define the square of this norm. Yeah, we are given the rho and sigma functional, and the alpha is between 0 and 1. This definition is okay, and the finite value. But alpha bigger than 1, this is not always defined. So we assume this. This case, we can define the same formula. Otherwise, we define plus infinity. Then the alpha Renyi standard alpha Renyi divergence is as usual given in this way. But QR quantity is in some sense the special case of the standard F divergence with function the power function t to the alpha bigger than or equal to 1 and minus t alpha. So the Q alpha quantity is written explicitly in this integral. So from the general property of the standard F divergence, we easily obtain the properties of the standard alpha Renyi divergences. So first one, this is alpha increases 1, the d alpha goes to the relative entropy, and also the alpha decreasing 1. If the d alpha is finite for some alpha bigger than 1, we also the convergence as alpha decreases to 1. And this d alpha is more increasing in the parameter alpha, and alpha between 0 and 1, we switch the alpha into 1 minus alpha, we have this the identity. And from the property of the general standard F divergence, we obtain the joint lower semi-continuity and the concavity convexity, or the joint convexity property, and the order relation, and the Mortonicity or data processing inequality under the internormal Schwartz map, and also the strict positivity obtained. So this slide is concerned the description of the alpha Renyi divergence in terms of the hanging up L1 element. So when the alpha between 0 and 1, we take the TR functional of the hanging up L1 element H rho to the alpha H sigma 1 minus alpha. Alpha bigger than 1, these three conditions equivalent. And the third condition, the eta appear here. So these equivalent, sorry. These are equivalent, and if eta is the formal expression, the eta is this part is moved to the left hand, and eta star eta is right this way. Then the Q alpha is written the same form. But H sigma is tau measurable operator, unbounded operator, and 1 minus alpha is here the negative. So negative power of the tau measurable operator is not well defined. Does not make sense. But in the formal sense, the same expression. And if you consider the TR function is the usual trace, and the H rho and H sigma is the usual density operator, then this QR quantity is the usual definition of the matrix case. So next, sandwich range divergence. But this topic is Anna Yenchova's the talk. So I skip this part. But this is anyway. This is not my contribution. And anyway, Beltashev Michel extended the sandwich range divergence to the phoneme algebra setting using the Araki-Masuda's LP norm. And Yenchova extended the sandwich divergence by using the co-circuit L alpha space. So in the general phoneme algebra, there are several different constructions. Hagelap LP space, Araki-Masuda's LP space, Kosaki's complex interpolation method LP space, and Hilsam's spatial the LP space. So there are 4 or 5 different constructions, but all construction is become the same Banach space, the same isometric isomorphic Banach space. So construction is very different, but the resulting LP space is the same. So I skip here. The remaining 5 minutes, okay? 5 minutes. 5. So last part is maximal F divergence. So first I restricted the rho sigma this class. So rho and sigma is the dominated each other. For such rho sigma, we can take the operator A, the reduced phoneme algebra, the support projection S sigma reduced. We take the operator A in this way, and A star A is the positive invertible operator in this reduced phoneme algebra. And we take functional calculus of f of A star A. Here the f is I assume the operator convex function on the positive half line. And this is the simple definition. This is maximal F divergence in this special pair rho sigma. Then we can define the restricted to this special situation. We can prove the Mortonist inequality and joint convexity. Then we take the eta under this condition, and we take this. This is from the joint convexity. This is a convex function of epsilon, so we can take limit. This is the general definition of the maximal F divergence. Then the Mortonist the data processing inequality and the joint convexity is extended to the general case, and we have the similar identity as similarly to the standard F divergence. We obtain this. And now in some sense second definition here, the rho and sigma general. Then the rho and the rho plus sigma. Rho is dominated by 1 by rho plus sigma. So we can take as before the operator A, and we take A star A spectral. We take a spectral decomposition. Then the maximal F divergence is explicitly written this integral. So this is our second definition of the maximal F divergence. And from this previous this integral expression, we can prove the joint row semi-continuous. This case, in the norm topology, previous standard of divergence is weak topology, but in this case, I can prove in the norm topology. And the martingale convergence similarly. And finally, following the Matsumoto's idea, that I consider the notion of reverse test. Reverse test is we take a sigma finite measure space, classical measure space, and map from polymodular M into L infinite. Then the triplet psi PQ. PQ is the classical L1 function. This is called reverse test. When this classical function P maps phi star to rho and Q to sigma. This case we call reverse test. And for again we take the operator A and the spectral decomposition, and we take the measure mu on the 0-1 interval, and by taking the Radon-Nikodym derivative, we can define the phi 0 map from M to L infinite on the 0-1 interval. Then the Fresier map phi 0 star given this way, and in particular when the function t on the 0-1 interval function t maps to h rho and 1 minus t h sigma. H rho and h sigma is the high map L1 element corresponding to rho sigma. So this phi not t 1 minus t is the reverse test. Moreover, for this reverse test, we have this maximal f-divergence is equal to the classical f-divergence. So this is a very nice reverse test. And from the Morton-Ritchie inequality for the maximal f-divergence, we obtain the inequality, this inequality obtained. But the previous reverse test is we call minimal reverse test. That is attained this maximal f-divergence. So we obtained this minimization variation, this variational expression. This is our third definition of the maximal f-divergence. And also from the Morton-Ritchie inequality for the standard f-divergence, we obtained from this immediately we obtained this inequality. And when the rho sigma is commute, the equality happened. So the typical example of the maximal f-divergence is the case of function f t long t. That is the Belapkin-Stavisky relative entropy. So even in the general polymodular setting, relative entropy is less than or equal to the Belapkin-Stavisky. And the matrix case, this is Umegaki relative entropy, and this is Belapkin-Stavisky. In the matrix case, the equality happens if and only if the rho and sigma commute. I strongly believe that this is also true in the polymodular case. Okay, this is a summary. So I give the systematic study of standard and the standard f-divergence and the linear divergence in the polymodular setting. That is the visit of the test case entropies based on the extension of the causal variational expression. And we have three different definitions of maximal f-divergence in the polymodular setting. The general convergence formula, the integral formula, and also the variational expression in terms of the reverse test. And I didn't explain, but the both standard and maximal f-divergence can naturally extend to the positive linear function on rho sigma on the general C algebra by using the normal extension of rho sigma to the representation, the generated von Neumann algebra by the whichever representation. When the rho and sigma has normal extension, and independently of the choice of representation. So we can take the GNS representation or universal representation, whichever. So even C-star algebra setting, everything can extend naturally. So thank you very much for your attention.
Any questions? Thank you very much. Any questions, remarks? Yes.
So do we have, I mean, we know we have sometimes recoverability, right? Do you have any guess how recoverability should look for maximal divergence?
In the von Neumann algebra case?
Whatever you can do.
Yeah, that is maybe next paper for our next paper. Yeah. At the moment, yeah, we have some idea, but not yet. Yeah, not yet well done.
The answer is yes. You have some idea.
Yeah, yeah, I believe. Yeah.
Okay. Any further comments, questions?
There is a paper by optimize the f-divergences. Do you have some idea how to extend it to this following algebra?
Sorry,
I mean this optimized f-divergence.
optimize the maximal f-divergence.
If I may repeat, Anna's asking the work by Mark Wilde on optimized f-divergences, whether that can be extended to the von Neumann algebra setting.
Optimize, I don't understand
optimized f-divergences.
We can talk about it later.
I don't understand what is the meaning of optimize.
We can.
Okay, yes, sorry.
Okay. So thank you, Dr. Hiai, once more, and we can go for the coffee break.